And now, moving on to the next part of our discussion on fluid motion, we take a look at the concept of ideal fluid flow, wherein now the fluid is in motion, whereas in the previous discussions, the fluid was in static case. So, ideal fluid flow. An ideal fluid is a fluid that exhibits steady, incompressible, non-viscous, and irrotational flow. So the fluid will smoothly flow as if in layers. We have what is referred to as laminar flow. Any obstacle that the fluid encounters, the fluid will smoothly flow around the barrier without rebounding and rotating. So it won't be turbulent. When it hits the barrier, it won't rebound and rotate. It would simply flow around the barrier. Smoothly flowing around the barrier, you have ideal fluid flow. Ideal fluid flow is described by two equations. We have the continuity equation and Bernoulli's equation. First, we have the continuity equation. The continuity equation relates to the flow speed of an ideal fluid in a container, pipe, or tube from one point to another. So as the fluid flows from one point to another, the continuity equation relates the flow speed of the fluid from one point to another. As the cross-section area of the pipe changes, the speed of the fluid changes. RV, which is the volume flow rate of the fluid, unit cubic meter per second, amount of volume flowing through a particular point in the container per unit time. So let's say you have a container. Say at this location, the cross-section area is A1. At another location in the container, you have a cross-section area A2. Say the fluid is moving from left to right. At the location of area A1, you have so many cubic meters flowing through it per second. You have the volume flow rate, R sub V. And R sub V is constant. Doesn't matter what location you look at. As long as you have an ideal fluid flowing through the container, R sub V is constant. So say you have 5 cubic meters per second. Doesn't matter where you look in the container, the volume flow rate of the fluid is 5 cubic meters per second. So 5 cubic meters per second here, 5 cubic meters per second here, and 5 cubic meters per second here, and so on. R sub V, the volume flow rate, is given by cross-section area times the speed of the fluid at that cross-section area. So, at area A1, you have A1 V1. At area A2, you have A2 V2. Then A3 V3, A4 V4, and so on. All of those volume flow rate will give you the same value because R sub V is constant. The same goes for mass flow rate. Instead of volume, amount of volume passing through a given location, you have amount of fluid mass flowing through a given point or location. You have mass flow rate R sub m, unit is kilograms per second. And just like R sub V, R sub m, mass flow rate is constant. R sub m is just equal to volume density of the fluid times R sub V. Since R sub V is constant and volume density of the fluid is constant for the most part, R sub m is also constant. Next, we have Bernoulli's equation. Bernoulli's equation takes into account the height and pressure differences as the ideal fluid flows from one point to another inside the pipe or container. Say you have a container. This time, the container is angled, say, diagonally upwards as shown in the figure. Unlike in the previous slide wherein we have the pipe. If you look at the cross-section areas of the pipe, there is no height difference in the centers of the cross-section area of the pipe. The continuity equation only considers the cross-section area and the speed of the fluid at that cross-section area. Bernoulli's equation considers not only the speed at the different locations of the fluid inside the pipe, it also considers the height differences and the pressure differences at the different locations of the fluid inside the pipe. So say you have a pipe such, fluid is flowing from one end of the pipe to the other end of the pipe. At this location, you have cross-section area A1. The speed of the fluid is V1. At location 2, area A2, the speed of the fluid is V2. At area A1, the fluid is applying pressure P on the walls of the container. At area 2, the fluid is applying pressure P2. So P1 at area A1, P2 at area A2 applied on the walls of the container. And then we have the height differences. At area A1, the height of the center of A1 is Y1, whereas in A2, the height is Y2. Bernoulli's equation tells us that for area A1, we have P1 plus 1/2 rho V1 squared plus rho GY1. At area A2, we have P2 plus 1/2 rho V2 squared plus rho GY1 squared. And the two sides are equal. You have Bernoulli's equation. Bernoulli's equation may appear familiar to you. That's because it's basically conservation of energy expressed in terms of the fluid flow. Diba? You have 1/2 mv squared, you have 1/2 rho v squared. You have mgh, you have mgy. So this is basically conservation of energy expressed in terms of the fluid flow, in terms of pressure and speed of the fluid as well as the height of the fluid. It has been observed from this equation, that the faster a fluid is flowing, the lower the pressure that it applies on the walls of its container. For simplicity, let's say Y1 is equal to Y2. So, rho g y1 is just equal to rho g y2. So, cancel that out, leaving us with P1 plus 1 half rho V1 squared is equal to P2 plus 1 half rho V2 squared. If V2 is greater than V1, to maintain the equality, P2 must be less than P1. The faster the fluid is flowing, the lesser the pressure that it will apply on the walls of its container. This phenomenon, the fluid applying less pressure the faster that the fluid is flowing, this phenomenon has applications in aerodynamics, for instance, in the design of the shape of airplane wings, as well as in the shape of cars. So we have Bernoulli's equation and continuity equation for the ideal fluid flow. Some problems only require you to use continuity equation. Some problems require you to use Bernoulli's equation. And then some problems will require you to use both the continuity equation and Bernoulli's equation. So please take note of that. And that's it for now. That's it for this video. In the next video, we'll take a look at a few examples. In the next video, we'll finish up our discussion on fluid motion. So once again, that's it for now. And thank you for watching.